Social distancing. Did you have a chance to look at the videos at all?
I was the YouTube channel, but I didn't actually want to do videos, but I did I don't know, two were ended, first two, but I didn't actually want to do them.
Okay, so you were able to get in.
But yeah, I just thought.
Okay. Okay, great. Yeah, I had to delete the other two because evidently YouTube allows you to post videos after 15 minutes. So I uploaded it, and then I got this message, and then they said, if you put in you send you a passcode, then it'll allow you to put longer videos. So I tried it, I put in the passcode, and I went back to the slash off. So I just deleted those two.
I saw that, but I just didn't.
Okay. It's nice if you want to kind of review something, just kind of go on. Okay, let's maybe do a quick sound check. If someone from the other end can sort of say something. Can you hear me?
Yeah.
Okay. Can you say something again, please?
We can hear you.
Oh, no, but I want to check if we can hear you. Can you say something again?
Yeah, testing, testing.
Okay. Hang on, let me check. Keep going.
A, B, C, D, E, F, G.
Okay, great, thanks. All right, you can hear, right? Okay, good. Okay, so let me first ask, were you able to get on and watch the videos at all on the YouTube channel?
I saw them, but I did not look at them.
Okay, if you can just test them, just sometime when you have time. You know, you don't have to watch the whole thing, obviously, but if you just see if you can watch a little bit of it, that would be great. And just give me some feedback on this. But what I'll do is I'll keep on posting them. So I think I'm like, after this class, I have 2 to post. So that won't be too hard. So then we'll have 7 total up. Okay? And I've been posting the notes too. So those should be on the ELC. Okay, let's see. So today, what we'll do is we will finish the section off on applications of linear systems. So I'd like to go over two other types of applications. One will involve networks, and the other one will involve sort of economic systems. So let's try to work on this. And if we have some time, maybe we'll talk a little bit about linear independence. All right, so again, let's look at applications. Linear systems. All right, so the first application I'll go over is the one on networks. All right, so there are various ways that you can sort of view this example. So let me first just draw you a directed graph and just show you how you can actually view this. All right, so I'm going to start with the graph. And it has certain nodes. So here's A, here's B, and here's C. Right? And there's certain arrows which actually go in and out of the graph. So maybe I should use a slightly different color here. Let's see. Let's do this green color. Okay. All right, so I'm going to draw some arrows that go in between these two. Okay, so out of A, I'm going to have an arrow which goes out this way. Okay, and at the end, I have 20 out here. Okay, so I'll explain this in a second. Okay, I have an arrow that goes between here, and this quantity is called x3. And then this quantity is, let's say, x1. And I have another arrow which goes this way into B, and that's x2. And then another arrow that comes out, that's x4. And then another arrow that comes in, and this is 80. Okay, can everyone see the graph? That's good. Okay, so so here's one way to sort of think about the graph. So let's say this is a graph which sort of depicts traffic around certain intersection points. So 80 could represent, like, for example, the number of cars going into sort of the intersection C. And x1 and x2 sort of represent the number of cars going out of C. All right. And then, for example, x3 represents the number of cars going from B to A. And then the quantity 20 represents the number of cars going out. Okay? So you have a certain amount of stuff going in, a certain amount of stuff going out, and then in between each of the vertices, you actually have certain amounts going through at any given time. Okay, so so we want to look at equilibrium. So let me just redo this. So the idea is we want to look at equilibrium. Okay, so what we want is the equilibrium happens when all the at each node the flow in equals the flow out. So the flow that goes in equals the flow that goes out. Okay. All right, so another way to think about this is this can sort of represent, like, for example, the amount of internet traffic, for example. It can also represent like a electrical currents. You know, you have like 80 something going into something and you have 20 something coming out. Okay. So this has applications to a variety of contexts. You can sort of use your imagination. All right, so if we want to actually look at equilibrium, we have to look at each node, and we have to sort of figure out what equation sort of governs each node. So let's look at node A, for example. Okay? So again, the number of things going in equals the number of things going out. So we have an equation. So what things are going in? X1 plus X3. How much is going out? Of A? Anyone?
20.
20, thank you. Good. All right, so this is how you get one equation. And now what we do is we just do this for the rest of them, right? So we take B, and let's look at B. What's going in? X2. What's going out? Anyone?
X3 and X4.
Good. All right. And we do the same thing for C. And similarly for C, we have 80 coming in, and we have X1 plus X2 going out. All right, so we have these equations. So what kind of equations are these? They're nice linear equations. Do we know how to solve this system of equations? Yes? No?
Yes.
Yes, okay, good. All right, so all we have to do is kind of write them out in a way that we can set things up in terms of AX equals B. So we have X1 plus X3 equals 20, okay? And then we have X2 minus X3 minus X4, that's going to be 0. And then we have X1, of course, plus X2 being 80. All right. So we have a system of equations. We can sort of think of this as AX equals B. Is this a homogeneous system or a non-homogeneous system?
Non-homogeneous.
Non-homogeneous, okay. Now we know how to solve this. We put this in the matrix form. Okay, so let's do that. So 1, 0, 1, 20. Okay, that's the first equation. Ooh, I think I have to do something a little bit differently here. Because there's not just 3 things, there's 4 things, right? Okay, so 1, 0, 1, 0. Okay, X1, X2, X3, and X4. Okay, next one, 0, 1, minus 1, minus 1, 0. Okay, next one is 1, 1, 0, 0, 80. Okay, so we have this. And now what we do is we just do Gaussian elimination, right? Okay, so now it's just turning the crank. Okay, so let me do that. Okay, so we want to multiply the first row by minus 1, add it to the third row, put the result in the third row. So 1, 0, 1, 0, 20, 0, 1, minus 1, minus 1, 0. And we have a 0 here. Next one's a 1. Next one's a minus 1. Next one's a 0. And then we have 60 down here, right? 6, 0. Everything good so far? Okay, now we can do the second one. Multiply the second row by minus 2. Minus 1. And then add it to the third row and then put the result in the third row. So we have 1, 0, 1, 0, 20, 0, 1, minus 1, minus 1, 0. And then we have 0, 0, 0, And then what do we have? A 1, okay, and then what's the last term? Anyone?
60.
60, very good. Okay, so this is reduced, right? Okay, so now the next thing is, so we have this in this reduced echelon form, like that. All right, so now we have to locate the pivots. So the pivots are precisely where the ones are, right? Here. Okay, the first non-zero entry in every single row. And so, do we have any free variables?
X3.
Good. So x3 is free. So x3 equals, let's say t is free. And now what we'll do is we'll just back substitute, okay? So the thing is x4 here has to be equal to 60. Right, that's what the bottom equation says. So x4 is fixed to be 60. And then let's see what we have next. We have x2 minus x3 minus x4, that's equal to 0. And so we have x2 minus t minus 60 equals 0. So x2 is equal to t plus 60. Okay. See, that's great. So let me box this equation. Okay, so we just have one more to go. Right? So that means that x1 here plus x3 has to be 20. Okay, so what is x3? x3 is just a free variable. So x1 plus t is 20. So that means that x1 is equal to, I'll just write it this way, minus t plus 1. Okay, any questions on this so far? All right, now let's just write the solution out. So the solution for the system is x1, x2, x3, x4. Okay, so x1 is minus t plus 20. What's x2? T plus 60. X3 is t, and x4 is 60. Okay? And then, you know, like always, we just separate out the t. So we have t. So this part represents the homogeneous system, right? So we have minus 1, 1, 1, 0. Okay, so that's a solution to the homogeneous system. And then we have a particular solution that we can read off of this, and it's what? 20, 60, 0, 60. Okay, any questions on this? Okay, of course, P is a real number. Now, there are certain things that we can sort of say about this. So first of all, the amount that's going in and going out is always positive. So we have some constraints here, namely that x1, x2, x3, and x4 are all bigger than or equal to 0. Okay, they're never negative. Okay? And so the question is, how big, for example, can t be? Well, so for example, if I take the top equation, so I need that. So x1 has to be bigger than 0. So that means that, so x1, let me just write it out. x1 is bigger than or equal to 0. So that means that minus t plus 20, this always has to be bigger than or equal to 0. Okay? So that means that t is always less than or equal to 20. Okay, so this always has to happen if, you know, the coefficients or the x's are all positive. Okay, so if T is bigger than or less than or equal to 20, then X2 is bounded, right? Okay, so X2, well, so I look at the second equation, right? And if T, the maximum T could be is 20. So the maximum of X2 has to be what? What's the largest X2 could be? If T can be no bigger than 20. Anyone?
80.
80, thank you. So X2 could be no bigger than 80. Okay, so no more than, for example, 80 cars can go through when we have this equilibrium state. Okay, now how about X3? Can we say anything? Yes, so we know that X3, the most it can be is what, 20? Ah. Most it can be is 20. Okay, so when you actually find all the equilibrium solutions, you can find inequalities which sort of state how big or how much flow you can have at most through any from one vertex to another at any time. Okay, so this gives you sort of bounds on, let's say, the traffic. It could be internet traffic or it could be actual cars if you want.
I have a question.
Yes, go ahead.
For X3, would you have to specify that it also has to be greater than 0?
Yes.
Like less than 20, but greater than 0?
Let's see, for X3, yes, that's right. X3 has to be less than 20. And it has to be certainly bigger than or equal to 0. That's correct. So if I want to put this other stuff in, then I can do that too. Okay? No problem. Good question. Okay, other questions on this? All right. Okay. So let's move on to the next application. So we've done balancing chemical equations, we've done networks, and now we'll do an application involving trading in economic systems here. So this is 2. All right. Okay, so the idea is that we are going to have 3 sectors. So let's call this economic systems. And we have 3 sectors. Okay, so we have chemicals. Okay, so I mean, this could be, for example, chemical plant. We have another sector is fuels. Okay. And another one is called machinery. Okay, so I'm going to shorthand this by C, F, and M. And the idea is that the chemical plant, for example, has a certain amount of output, and it's going to give some to the fuels, and it'll give some to the machinery, and then it'll keep some for themselves. Okay. Okay, so let me just go up. So the idea is that chemicals, so 30% of the output of their output goes to fuels, and 50% of the output will go to machinery. And then they'll actually keep 20%. Okay. All right, so that's the first one. And then fuels does kind of the same thing, except in different percentages. So 80% of the output will go to chemicals. Let me underline these. And then 10% of the output will go to machinery, and then we'll retain the rest. So it keeps 10%. Okay. And now I just have to tell you what the machinery part does, the machine shop. Okay, so 40% of the output goes to chemicals. 40% goes to fuels. And then retains the rest. Okay. All right, so what you can do is you can sort of make a table. So this is called distribution of output, if you'd like. And then let me just draw a little table here and draw straight. Okay, so let's see if we can do this to make it clear. All right, so I'm going to draw a little table. Okay. All right, so let's look at chemicals. Fuels and machinery. I'll add a little extra row here. And this is obtained by. Okay.
What does that last part say again?
Oh, it says obtained by.
Okay, thank you.
Let me make it a little bit more clear. I'm sorry. Okay, so I'll write it a little bit more clear. Okay, so this is okay. Maybe it's a little bit better. Sorry.
Yes, thank you.
Okay. All right, so let's look at chemicals here. Okay, so how much does chemicals keep? It keeps 20%. So what I'll do is I'll put a 0.20 here. And how much is it obtained from fuels? Actually, let's see. I'm going to do it this way. Okay, so let's see. Yeah, I want to write it this way. Sorry about this. Maybe I'll change this. I apologize. Okay. So retains 20%. 30% goes to fuels, and 50% goes to machinery. Okay. So let me just erase the obtained by. It's maybe given out by. That's a better thing. Okay, so let me just erase that. Sorry about that. Let me just erase this. Okay, so I'm just gonna put the information above in the table. Okay, so let's do that. Okay, so now the next line is 80%. Okay, and this is through the fuels. Okay, and then how much does it actually retain? 10, it's 10 extra. Okay, and then finally, let's see, machinery. Bring this guy back. So 40% chemicals, 40% fuels, and 20%. Okay, so you can actually make a table like this. It's called an exchange table, just so that you kind of keep everything straight. Okay, so now what we have to do is we have to sort of look at equilibrium. So equilibrium happens So you have the amount of output, total output, goes like this. Well, it's 2/10 of C plus 3/10, let's give it an F, plus 5/10 of F.
Okay, so this is the way you sort of make the equilibrium chart.
Okay, so then how about the amount for fuels? My connection, I think, is making this happen. So fuels, we just run down the chart, 8/10 C plus 1/10 of F plus 10. And then M is equal to 4/10 C plus 4/10 of F plus 2/10 of F. Okay, so now what we can do is we can try to find, how much output each one has, C, F, and M, by setting up a linear equation, system of equations. All right, so what I should probably do is I should multiply each equation by 10. So let's multiply each equation by 10 so we can clear the denominators. And when you do this, the first equation becomes the following. So you get 0 is equal to minus 8C plus 3F plus 5M. Does everyone see why that's true? Because if I multiply the first equation by 10, I get 10C plus 2C is equal to 2C plus 3F plus 5M. So you're bringing the 10C over, and with the 2C, it becomes minus 8C. Okay, it's just, arithmetic. And then similarly, you do it for the other ones too. So 0 is equal to 8C minus 9F plus M. And then finally, you get 0 is equal to 4C plus 4F minus 8M. Okay. Great. So is this a homogeneous system or non-homogeneous system?
Homogeneous.
Homogeneous.
System. Okay, good. So this is the homogeneous system of equations. All right, and we know how to solve this. We just put it in our little machine here. Okay, so all right, so let's see okay, so what I'm going to do is I'm going to reorder these just to make it a little bit easier to deal with. So I'm going to put the first one on top. It doesn't matter which order you put the equation, right? The system is the same. So I'll put the 4 up here just so I can do cancellations easier. 8 minus 9, 1, minus 8, 3, 5. Okay, so I can put the last equation up there because when I try to do Gaussian elimination, that pivot is a lot easier to work on. Okay, so let's do this. Okay, so I'm going to multiply here by minus 2. And I'm going to add it to the second row and put it in the second row. So 4, 4, minus 8, 0. I get it 0. Minus 9, minus 8, that's minus 17. Okay, and then we have 1 plus 16, that's 17. And then, of course, whenever you have a homogeneous system, I mean, the B's are always going to be 0 in the process. Okay? You don't have to really worry about it so much. Okay, so now I want to get rid of this thing over here. So I'm going to multiply the first row by 2, add it to the third row, and then put it in the third row. Okay, so this I get 0 here. The next one I get is 8. Plus 3, that's 11. And then I get minus 16 plus 5, that's minus 11. I get 0. Okay. I can do one more step. So just to make it cleaner, I'm gonna divide here, divide by 4 on this row. I'm gonna divide by 17 here. And I'm gonna divide this one by 11. Okay, just to clean it up. Okay, so let's do that. So that's gonna be, divide by 4, that's gonna be 1, 1, minus 2, 0, 0, minus 1, 1, 0. Divide by 11, get 0, 1, 1, 0. Okay, and then it's easy to see that when I do Gaussian elimination from the second row and third row, I'm going to knock out the third row. Okay, so there's 1, 1, minus 2, 0. And I get 0, minus 1, 1, 0. And I get 0, 0, 0, 0. Okay, good. Am I, again, am I going to have finitely many solutions or infinitely many solutions? Anyone?
Infinitely many because of one free variable.
That's right, infinitely many. So let me go back up just to make sure. So the first column represents C, F, and M. Okay, so we kind of have to keep track of what companies represent each single column. All right, so the free variable, we'll let M be the free variable. Okay, so this is free. Again, because the pivots are right there. So the non-pivot column is the free variable, corresponds to the free variable. Okay, now we'll just, do what we normally do. So minus F plus M is equal to 0. And so that's the second equation, obviously. So minus F plus T is 0. Okay, so what's F? F is minus T. Or F is T plus T. Now let me just erase this. Sorry about that. Okay, that's better. Okay. Okay, so MST, FST, and then we do the last one, right? So last one is C plus F minus 2M is 0. Okay, so let's plug everything in. F is T minus 2T equals 0. C minus T is 0. So it turns out the C is T also. Okay. All right, so here's our solution. So if I take C, F, and M, this is going to be the set T, and then I have 1, 1, 1. Okay, so this is T and R. Okay, so the equilibrium happens whenever all the outputs are the same. So you want to set the equilibrium price so that all the outputs are the same for each of the companies. So equilibrium happens. Okay. Good. All right, so any questions on this?
So we specifically looked at the outputs, but if we looked at the inputs, would we get the same solution at the end?
Well, basically, it's just a redistribution of things. That's what we're really looking at. I
Okay.
guess if you want to say input, yeah, you can say inputs too. This is sort of a model that can kind of be used in various contexts. You know, the amount you actually redistribute, for example, you kind of want to see what happens with the linear system. Later on, what we may do is we may do an application involving like economic aid to countries. And what happens is we look at things over a yearly period. So we see how much happens after 1 year, after 2 years, after 3 years, after 4 years. And then later on, you know, with this linear system, we'll see what happens in the limit too. Okay, so there are various ways that you can sort of apply this, you know, in certain time increments or whatever. Good. Questions? Good questions? Okay, good. So we have a little bit of time, so we can start in on the next section. I know we're not going to meet till Wednesday, so I hope everyone has a safe and happy holiday weekend. Please do be mindful of social distancing and masks. Okay, so let's start in for the last 11 minutes or so. We can talk about linear independence. Okay, so let's talk about linear independence. This is a concept which is sort of the opposite of spanning in some sense. And I'll make that more precise later on. But right now, I just want you to get a feel for what linear independence means. Okay. So let me draw you a picture. Like this. All right, so if I take two vectors, let's call them v1 and v2. The idea of being linear independent is that you really don't want one vector to be a linear combination of the other vector. So in this example, you know that v1 and v2 are not on the same line. So neither of them is a linear combination of the other one. So in this case, the set v1 and v2 are linearly independent. Okay, so we'll just start off with some examples. Now, let's say I take the same plane, like this. Okay, so I'm going to take v1 and v2 again. But what I'm going to do is I'm going to throw in another vector in the plane. So let's call this v3. So can any vector be written as a linear combination of the other ones? Yes or no?
Yeah.
Yes, right? Like v3 could be written as a linear combination of v1 or v2. Also, v1 could be written as a linear combination of v2 and v3. So these vectors here, v1, v2, and v3, are not linearly independent. Okay. All right, so let's go up one more dimension. Okay, so let's look at actual 3 space here. So this is 3-dimensional space. Ooh, I do not want to put arrows on my coordinate axes here. Okay, so let me redraw this without any arrows. All right, so this is a three-dimensional space. Okay, let me take vectors here. Let's add a little pizzazz to this. Let's make them colored. Let's take the vector v1, and I'm going to take the vector v2 over here. And let's say I take the vector v3, which goes sort of in a different direction than v1 and v2. Okay, so if I take these three vectors, are they linearly independent or not? So you ask your question, is v3 in the plane spanned by v2 and v1? Yes or no? Anyone?
No.
No. Okay. Is v1 in the plane spanned by v2 and v3?
No.
Okay, and similar with the other one. So v1, v2, and v3 are linearly independent. Okay. Now, finally, let's do one more example, and then I'll actually state what the definition is. Ooh, no. Better. Okay. All right, so I have vectors v1 here. I have vector v2 here. The v3 goes in sort of a direction which is not in the span of v1 and v2. And then I add one more vector. Let's add the vector v4, which goes here. Okay, so add one more vector to this set. So do you think this set is linear independent or linearly non-linearly independent?
Well, if we have three vectors and they span 3 dimensions, wouldn't each vector be able to be like a linear combination of the other?
That's actually true. So v4 can be written as a linear combination of the other three. Okay, and also for the other ones. So the conclusion is these vectors are not linearly independent. Okay, good. All right, so here's some examples. All right, now that's all fine and good. Oops. But you may want to ask yourself, well, is there a way that we can check? Like, let's say I have a zillion vectors, and I want to know like whether they're linearly independent or not. I want a way to actually check whether the answer is yes or no. So let me write a definition out and show you that it's quite doable. So a set of vectors v1, v2, up to vt, let's say in Rn, is linearly independent. Okay. If and only if given C1 V1 plus C2 V2 plus CT VT So if you have the linear combination of any of these vectors being 0, then the coefficients have to be 0. Okay. So this is a way to check linear independence. So you want to see if whenever you have a linear combination being 0, the vector actually has to be the 0 vector. Okay. So it's linearly independent if this is true. Otherwise, the set V1, V2, up to Vt is linearly dependent. Okay. All right. All right, now let's use our imaginations a little bit. So if I'm given a bunch of vectors, maybe like 3 or 4 vectors, and I want to know whether they're linearly independent or not, how can I actually do this? How can I check? Does anyone like can tell me a way to do this?
You add them?
I can what?
Can you, like, do you add them and then see if it's 0?
So let me kind of lead you through this. So I think you're thinking about the right thing. So suppose I put my vectors here in the columns of this matrix. Okay. So when I have a linear combination being 0, so C, the vector is C1, C2 up to CT, then I get A times C is equal to what? So this equation here is the same as what? A times C being what?
0.
0. Good. Ah. Do you know how to like solve this at all?
It's a homogeneous.
The homogeneous system of equations. All right. So the vectors are linearly independent if the only solution to the homogeneous system is the 0 vector. So I can now state this. So okay, so let me just say it this way. So the vectors v1 up to vt are linearly independent if and only if the only solution to the homogeneous system AC being 0 is C equal to 0. Okay, so what you can do is you can set up the homogeneous system of equations, and then what you can do is just use Gaussian elimination, and then if the trivial solution, meaning the 0 solution, is the only solution, then the vectors are linearly independent. If you have free variables, what can you say? If you end up having free variables, what can you say? Anyone? So let's say I have this homogeneous system, and let's say I have some free variables at the end. Are there finitely many solutions or are there infinitely many solutions?
Infinitely many.
Okay, they're infinitely many. If they're infinitely many solutions, are the vectors linearly independent or linearly dependent?
Dependent.
Linearly dependent, right? Because you have other solutions than C equals 0. Okay, so you can actually look at this and you can put it in the matrix form. We'll do this, we'll do lots of examples on Wednesday where we use the homogeneous system to see whether vectors are linearly independent or linearly dependent. Okay, so I will stop here. Are there any questions on this?
I had a question about our next homework. When exactly is that the next homework due?
I want you to shoot to have it done either one. I know this has been like a holiday weekend and stuff. I like to, optimally, Wednesday would be good, although I may extend it to Thursday on this week, on this base.
Okay.
Okay? All right. We should be done with all the material for this homework set too, so. Okay. Any other questions?
I have a question about how this relates to span.
Yeah.
So you mentioned earlier in one of the earlier lectures that the homogeneous span is null space or whatnot. So we're essentially trying to figure out here that the only solution is the null space solution. And if that's true, then it's linearly independent.
That's
Is
right.
that correct?
So,
Okay.
So now I think you're asking a great question. So remember, B is in the span of these vectors. If and only if AX equals B has a solution.
Right.
So both concepts reduce down to looking at systems of equations. Okay, so to verify one condition or the other condition, it's a different statement about systems of equations. Does that make sense?
Yes, it's just kind of like a different perspective of looking at it. The same thing.
That's exactly right. I mean, we have this kind of abstract concept, and what we're doing is we're bringing it sort of down to earth by using matrices. Yeah, exactly.
Okay, thank you.
Okay, other questions?
So which day is next?
Oh boy. Okay, so let's see. So 7 lectures have been up. Is that right? Yeah. Yeah. So we've done 7 lectures. So this will be number 8. So I guess let's see. I guess this will be. Yeah. That's right. That's right. Now let me just say that we've had sort of reasonable class, in-class attendance. If you happen to want to sit in on a day, you can try, and most likely you will be able to sit in. So just let me know beforehand. Okay. Okay. Other questions? All right. So I wish everybody a safe holiday weekend. We'll see you on Wednesday.
You too, Mr. Doctor.
Thank you.
Thank you.
Okay, thanks. Oh, so, sorry, I don't know if I answered the question. Let's see, so I think it's